Product teams launch features that look promising and then watch their metrics drift back to baseline because they mistook noise for a real effect. The specific misunderstanding is believing that a measured difference is a fact about the world instead of a quantity that would vary if you sampled again. Because of that, they ignore the distribution of the statistic under repeated sampling, and they silently swap the roles of data and hypothesis, pretending the data tells them the probability the claim is true. Picture a dashboard spike after a campaign, the room aligns on a victory narrative, budgets get committed, and only weeks later the metric slides back while the quiet cause was ordinary randomness that no one checked. Here's the clean idea. Hypothesis testing is a structured way to ask whether data you saw is plausible under a baseline story where nothing interesting is happening. You write down that baseline story, often called the null, and you choose a summary of the data that would separate signal from noise if there were signal, called the test statistic. Then you ask, if the baseline story were right, how often would I see a statistic at least as extreme as what I observed? If the answer is rarely, you treat the data as evidence against the baseline story, not proof. Evidence, calibrated by how rarely such a result would occur if there were no effect. Take a familiar situation, you change a subject line on an email, and the initial sample shows a bump of about 5% in opens. You're tempted to declare the new line a winner and roll it out. Hypothesis test pauses that impulse and asks a different question. Suppose there were no true difference, and the apparent bump came purely from who happened to be in the sample. How surprising would this gap be under that no-effect world? If that gap would be routine under the no-effect world, you treat the bump as noise. If that gap would be rare under the no-effect world, you have evidence worth acting on. Beginners often treat the test as a verdict on truth. They think a small tail probability means the baseline story is unlikely given the data, or even that it is false. They rate a star or a keyword and stop thinking about how the data were generated. They peek at results again and again, picking the moment the result looks favorable and assume the label from the test still means what it claims. That mistake is expensive in ordinary ways. It pushes people to launch changes that only looked good because of timing or luck, and it shuts down good ideas because early samples swung the wrong way. It damages trust in experiments, since nothing seems to replicate and people start to think the method is theater. The correction is unglamorous and specific. Write down the baseline story before you look, pick a test statistic that matches the effect you care about, decide when you will stop, and define the rule you will use to make a call. Then follow it. You will notice I'm talking like this is a decision rule rather than a proof engine, and that is the right frame. In practice, you set a threshold that says, if this result would be this rare, or rarer under no effect, I will call it evidence and change my behavior. A classic choice sets that rarity near 5%. That sentence has a concrete cost baked in. It means that even if the world has no effect, sometimes your rule will still shout win, roughly at that rate. You do not get certainty. You get controlled risk of being fooled, and you accept it knowingly. Behind the scenes, the math is simple in shape, even when the details vary. Under the baseline story, your statistic has a distribution that describes its wobble from sample to sample. For an average, repeated sampling produces a bell-shaped spread around the true average once the sample is large enough. For proportions, the spread can be calculated exactly from the way counts fluctuate or approximated by the same bell-shaped curve when conditions allow. If you do not trust theoretical approximations, you can simulate the no-effect world by shuffling labels or resampling from the observed data in a way that honors the baseline story and read the rarity directly from the simulated spread. Now to consequences people overlook. If you keep looking at the data until it looks favorable, you are changing the game while pretending the rule stayed fixed. The test assumed you would look once after following your stopping rule. By glancing early and often, you invite the most extreme swings to catch your eye, and you label them as evidence. If you test lots of variants or metrics and only report the best-looking one, you are playing the same trick in parallel. The method cannot protect you if you change the questions after you see the answers. The fix is mechanical. Pick your stopping rule before you start, whether it is a fixed horizon or a clear, justified decision boundary designed to handle peaking. If you must look along the way, use a method built for monitoring that keeps the overall false alarm rate where you promised it would be. When you try many ideas at once, adjust your standard so that the chance of crowning at least one false winner stays under control. Or split your data so that discoveries made in one slice must clear the bar again in a fresh slice. None of this is fancy. It is just refusing to make the math answer a different question than the one you set it up to answer. Another blind spot is power, which is the ability of your test to notice a real effect of the size you actually care about. People run tiny experiments, get a noisy result, and then act surprised that the sign flipped the next time. Or they insist on a threshold that is very strict without giving the sample size needed to make real effects visible under that standard. Planning is straightforward. Decide the smallest effect that would change your action. Estimate how much your statistic tends to vary given your measurement process, and collect enough data that a real effect of that size would typically push you past your rule. Then if the test does not cross the bar, you will know you did not merely underpower it. Do not confuse statistical detection with practical importance. A test can say the result is inconsistent with pure noise, while the size of the change is too small to matter for your goals. That is why hypothesis tests pair well with intervals that state a plausible range for the effect. If that range is narrow and well away from no effect, you can plan confidently. If that range is wide and crosses no effect, you learn that your data do not pin down the magnitude, and the right response is to gather more information or to accept that the effect, if real, is too small to worry about. Decisions need both the yes or no from the test and the how much from estimation. Under stress, keep the mental model clean. You are comparing data to a world where nothing is happening, using a statistic chosen to be sensitive to the pattern you would expect if something were happening. You translate the position of your observed statistic into a frequency statement about how often such an extreme would arise under that quiet world. Then you apply the rule you committed to, knowing exactly how often it will mislead you if the quiet world really holds. If you change the rule or sift through many attempts, you must update the frequency statement or stop claiming it applies. The single shift to keep is this. Hypothesis testing is about the behavior of a procedure under repeated use, not about certifying truth from a single sample. Treat the test as a decision tool with an advertised long-run error rate, not a confirmation stamp. Write the baseline, write the rule, run the procedure as written, and let the data vote under that contract. Next, we pin down the quantity that most people trip over when they run this procedure in the lesson titled "P-cell p-values explained without the confusion."